Okay, so the screen should be recording. This is going to be a recording of chapter one. So I typically start the week with the objectives. Go ahead and just duplicate that slide. And this week we had done the introduction, syllabus information, chapter 8 lectures, or chapter 1 lecture, and then chapter 8 later on in the week. Cool. So this is the PowerPoint lecture for chapter 1, title of What is Science? We had a class activity where you were asked to describe an object and send that description back home with the assumption of them not really knowing like anything about Earth. So say if I was trying to describe like a hair pump, right? I would maybe say something along the lines of some sort of vessel that does not spill water when tipped and has some sort of lid. There's a mechanism that when pulled releases the liquid held within the vessel out into the air in fine particles. I might also mention something about there being like a tube that is suspended in the liquid, or I might refer the color of the pump to something I recognize from home. I might say that instead of like a vessel, I might say it looks like a cup or a bottle, but whatever, my alien language would include for that type of thing. The point of this activity was to describe properties of items because the way we describe and observe the world is through properties such as the things we see with our senses, so smell, sight, hearing, touch, taste, as well as comparing an object to something else. And that's typically called a referent. So when I was trying to compare the spray pump to like a cup or a bottle, I was using a referent to kind of refer what's something we know to something that is new to us. For example, if you ever have the experience of eating a cricket, someone might encourage you by saying, "Oh, it tastes just like chicken," as kind of a referent to something that you already know the taste of. Some challenges that we experience with this is that what I might know and understand is not something that someone else might know and understand. If I say my book is olive tone, others might not know what olive tone is or what that looks like. Or if I say something smells like a specific perfume, but no one else has smelled that perfume, they're not going to be able to kind of understand that reference. We get around this problem by having measurements. And then in this case, the referent is something that we all agree upon, and that is what we call a unit. Any good measurement should have a number or a value and a referent unit. And then this image just sort of shows like a fun thing that I think is very cool. So a lot of the English system standard of measurement is actually based on different body parts. So like our thumb's about an inch, or part of our thumb's about an inch. The wingspan between your nose to the tip of your hands. The average person's like that was meant to be a yard. A foot you meant to be like the size of your foot. And that was how people use those reference. But of course, everyone's like hand and foot and arm are going to be different lengths. So at some point in time, we kind of made those standardized. The key point of this slide is that a good measurement needs to have two parts, a number and the unit. So if you have a measurement that's just a number, it tells us absolutely nothing. If it's just a unit, again, it tells us absolutely nothing, except for maybe what we're trying to measure. But you need to have both in order to know how many of those units are in your measurement. So if I say like my pencil is about, say, 5 inches, right? But if I just said 5, I don't know if it's 5 centimeters. I don't know if it's 5 feet. Granted that it's pencil, it probably won't be feet. But the combination of having a number and a unit is what makes a good measurement. We kind of played a little game about measuring the horse and if how many like feet or inches it might be. We talked how the English measurement is kind of based on body parts, but in science, we've developed our own standard units, which we call the SI base units, and they are the ones that you see here. And it's also important to note that any scientific unit, even if it doesn't have the symbol directly, is based off of these symbols. So, for example, if we go into forces and we're dealing with newtons, that's going to be like meters over second squared times the mass kilograms. So even though it's a new unit, it's based on these SI base units. So these are just some good units to kind of know and be familiar with. Again, English system based on human body parts, metric system was established later in an attempt to get a very universal system of measurement. This slide just emphasizes that our standard metric units come from something that is easy to replicate. So, for example, time is referred to the oscillation of cesium atoms and the multiplication of that, something that's always going to stay constant. So we can always kind of refer back to that if needed. This stuff doesn't really matter for the level that we're doing it at, but if you get into like really, really deep quantum mechanics and things like that, a slight change in what a second means could kind of greatly interrupt your calculations. Another great thing about the metric system is that you move up and down sizes by adding or dividing by tens, multiples of tens. So you can kind of just move the decimal points around in order to get the value that you're looking for. And let me see if I can write on here. So let me do it. And the thing that I like to kind of use, like this one is maybe not the best slide for it, but I'm gonna put it here for now. I like to use a little like prefix thing. So King, which is K, Henry died, but I could probably type this. Yeah, I'll save this for later. I'm sure it'll come up later on. Let me just check. No, I guess I'll do it there. Okay. I like to do King Henry died base unit by drinking chocolate milk. And then what this allows us to do is just move back and forth between the different measurements. So like one hop is 10, a multiple of 10 for each hop. Or you move the decimal once. So like say if I was going from kilometers to, let's do centimeters. And we'll say it's like, I'm just gonna do 1, 2, 3, 4, 5.6 kilometers. And that's gonna probably become, go ahead and grab our thing. I can change the color on this. Go, it's one hop, two hop, three hop, four hop, five hop, centimeters. So that's gonna be one hop. 2 hop, 3 hop, 4 hop, 5 hop centimeters. So then our kilometers would become, and I probably moved the decimal tooth far back for this example, but oh well. 5. So then it's 6 as 1 hop, 2 hop, 3 hop, 4 hop, 5 hop centimeters. Right? Because that's 1, 2, 3, 4, 5. And then for a better example, see if I put this up here. We'll do 9 point. Still 2 kilometers. And we'll still change it to centimeters. So then we had 9, and then it's 1 hop, 2 hop, 3 hop, 4 hop, 5 hop, point, whatever is left over, centimeters. Right? Because it moved over 5 times. 1, 2, 3, 4. 2, 3, 4, 5. My hops aren't drawn very well. But you get the idea. And then another way of saying that is that 1 kilometer is equal to 1 and then 1, 2, 3, 4, 5 zeros centimeters. So then if I wanted to convert between the two, I would just, in this case, multiply by the numbers of centimeters because we're trying to cancel out the units. This is a lot easier to do on the board. See if I can just do our number. Kilometers. And then we would multiply that by our 1 kilometer. Divided by this number, centimeter. And the reason we do that is just to be able to cancel out these 2 kilometers, and I didn't even finish writing kilometer. Sorry, writing like this kind of sucks. Then I can just cancel out the 2 kilometers, and that's what allows me to change units. So then in this practice exercise, we'll look at the size difference between the powers of 10. And then the main thing to note is that negative numbers, like this one, are smaller, whereas positive numbers are bigger. So in this case, we have between 0.6, 10 to the power of 6, and 10 to the power of 5. They're both positive, so we're just looking for a bigger number, so 6 is bigger. This one, they're both the same number 6, but there's a negative, and the negative is going to be a lot smaller. So this one's again bigger. And then we have -6 and -5. In this case, the more negative you are, the smaller you are, so it's actually the -5 that's going to be bigger. Then again, 0, which just means it's going to be a 1. And then 10 to the -5 is going to be a lot smaller than that. So it's that. And then this 10 to the -2 is going to be the same as 0.01. Because if you think about it, it's going to be 10. And then that -2 means you move the decimal over this way. So it's smaller twice. But it's actually typically written as like 1 times 10 to the -2. So the more accurate representation of this would be like 1 times 10 -2 becomes 1 divided by 10 to the 2. 10 to the 2 means there's 2 zeros. So that's going to be 1 divided by, and then it's 1, 2 zeros. And if you plug that into the calculator, you get this. Yeah. Or you just know that like when you divide by something to the zeros, you move it over twice. So see, it's typically there, then you move it over. 1, 2. And then you put a decimal point and put a zero between those. All this to say that this one's going to be larger. And then if we go on to the next one, it's just a conceptual practice problem of like which one's bigger and smaller, just to help you get an idea of centimeters versus meters. Yeah, meters are going to be larger than centimeters. This is more practice of what we saw previously. This just has the answers, and it's the same problem, so. Then this is the same idea, but applying just the metric to the weights, right? So kilograms is going to be larger, and then grams is kind of our base unit. Milligrams is smaller. Because remember again, if we do our little mnemonic, King Henry died by drinking chocolate milk, and it goes larger to smaller. Then we can go ahead and look that kilograms is going to be our largest value, which is probably going to be our bear. Milligrams is going to be our smallest, which is going to be our B just because it's smaller in real life. And then grams is going to be whatever's left over. Nope, then they stay there. These are some practice problems. Let me see if I can clear. Where we're going to move things over, around. You did pretty good on the homework. So I think there shouldn't be too much issue, but I'll go through them just be safe. So again, King Henry died by drinking chocolate milk, just for our reference. You have 30 centimeters turning into meters. So that's going to be centimeters to our base unit. Going to hop over twice. So 1, 2. End up is 3 meters. 5 kilograms to grams. Grams is our base unit. So 1, 2, 3. Do 1, 2, 3. Every hop that we add is just going to be adding up 0. So it's going to be 5 and then 2, 3 grams. Kilometers to meters, same kind of concept. 1, 2, 3. Probably type that one. 1, 2, 3. Milliliters to liters. Milliliters is smaller. So we're gonna hop over to liters, which is our base unit. So that's 1, 2, 3. 1, 2, 3. 0.5. Just so you know, a good way to know it's your base unit, it doesn't have a prefix. So for example, we have centimeter, millimeter, kilometer, and I guess you could probably even do like hectometer and stuff like that. These are the main ones we could see. And then the base is just meter. Same thing for liters. Have like kiloliter, milliliter, centiliter. I guess those two are the ones that we usually see. Base, liter, second, millisecond. Those are probably the two ones that we see. That's just like a good little thing you can use to remember. Between 25 kilograms and milligrams is a kind of a big jump. So as we go basically the whole round. So 1, 2, 3, 4, 5, 6. So 6 hops. And we can actually get around this by just doing times 10 to the power of positive or negative 6. Because we're going from larger to smaller, it's going to be positive 6. Because the smaller unit is going to have more zeros. That little symbol there just means plus or minus. And I'll write that in. Or I'll type that in later. In this case, it'd be 25 times 10 to the power of 6 milligrams. And similarly, it's from centimeter to kilometer. Same concept, just in reverse. So let's see, I'll do pink. All right, so we have centimeter, 1, 2, 3, 4. This time it's 5. Minus 5. And this time, because we're going from smaller to larger, see if I can just type that. Smaller to larger units, so you're going to be removing. It's the same number, but because you're changing the unit, you need like less zeros to be the same amount kind of thing. So in this case, because it's, let me go back to writing. 10 to the 5 centimeters. Is- And in this case, because it's basically saying that like 1 kilometer equal 10 to the 5 centimeter. You can go, this is this times 10 to the 5 centimeter, or 1 kilometer. And then both sides kind of cancel out and you get your answer of 1 kilometer. Again, any measurement should have the number and the unit. So that's just one. Alternatively, you could have also just written it as 10 to the 5 centimeter times 10 to the negative 5. And then the two top numbers, you just add. So 5 plus 5, 5 minus 5 is 0. 0, which gives you 10 to the 0, which is just 1. You get the same answer that way. I guess it's fine that they're overlaid. You can kind of check the numbers. Let me. So again, 3 meters, 5 with 3 zeros. I might have done the milliliters wrong, it looks like. 25 times 10 to the 6, and then just 1 kilometer. Let me go back and see about those milliliters to liters. This looks like I did that part wrong. 1. Oh, that's right. 2. I guess I have to double check that. These do come from a previous professor, so it might just be a typo. One, two. Oh. Um, Ratios relate things to one another. For example, we did like a tally of how many of us drink coffee and things like that. And then it's like, say 5 students. So 5 students drink coffee out of 7, so then your ratio is 5 out of 7. We use ratios to convert between things. So one that we'll use a lot or that is very common is density, which is just a ratio of mass to volume. So you do mass divided by volume. The units of this is usually grams per centimeters cubed or grams per milliliters. Either one works. We did this with our eggs, where we kind of weighed the egg and then we found the volume of the egg by subtracting the difference in water volumes before and after adding the egg. And that just kind of gives us a better idea of um just how much volume the egg was instead of trying to like measure the circumference and then calculating the volume that way. The main thing with this slide is knowing that density is how heavy something is, depending on how big it is, or compared to how big it is. So if you have something really dense, it's going to be small but heavy. If you have something not dense, it's going to be maybe not so like big but light. And then, yeah, don't forget also that a good measurement should have a number and a unit. So if I wanted to write density in a proper way, I would have to write like, I could do like 5 grams per milliliter, and that'd be a good measurement for density, right? Because you have your number and your unit. Good. And then unit is just your number. Your reference number. Yeah. Ratios tend to be fractions or have a colon between the two or an equal sign. Just to say that they both, the equal sign is saying that they're both the same thing, just with different units. And then the colon is just saying like it's a ratio, this. Density again is a fraction. So this over this. There are just different ways of saying ratios. The one with the equal sign is the most likely to be your conversion factors. So if we are like changing units, this something with an equal sign is what you use the most. But you can definitely convert using like colon or a fraction as well. This was the homework. This is just solving the volume of a cylinder. You do that by kind of plugging in the different numbers. So in this case, we have 30 centimeters for the radius, which is our r squared was there. Probably not cover the squared was there. And then height 5 centimeters. It goes into your height. Pi is just a number you can put into your calculator. It's a kind of constant. So I can't, I'm typing this, so I can't really do that on the computer. 30 centimeters. This up sign just means it's to the power of 2. And then I'm going to do a space to show that it's separate. And then our 5 centimeters. And probably even calculator. If we do this out of the way. No, I cannot. There we go. We do pi should be somewhere in here. There's this pi times parentheses 30 to the second power times 5. And that gets us our big old number there. And then that's our volume. Is it square root of 30 or the power of just square root? Let's do that one first. 30. Okay. Yeah. It's just plugging it in, put it into your calculator. Your symbols are kind of your way of defining your unit. They represent like the quantity and what measurement you're using. And the equations are relationships between properties. So we'll see a few of those, for example, Planck's equation, which looks at the energy of a photon based on Planck's constant and frequency, things like that. The density equation that we saw defines density in relationship to mass and volume. So yeah. Data is the measurement of information. So we collected data, for example, when we were doing our egg experiment, we collected like the volume, the weight, those were quantitative data because they dealt with numbers. We also had qualitative data, which was like how it feels, how does it look, how does the light act through it. Qualitative and quantitative, I don't know if it covers it in here, it does not. But it's just like num with numbers or with explanations. We use this measurement to kind of describe conditions, events, any changes, and it's just a good way to kind of keep track of everything. Science kind of began 300 years ago. Often think of Galileo Newton, Isaac Newton being our first true scientist because any philosophers didn't really like test the theories, they just kind of thought about them. And it was Galileo Newton that kind of got that component of experimental science or experimental evidence, which is part of our modern scientific movement. The main methods of the scientific method is observing, using that observation kind of propose some sort of explanation or even a question about what we saw. Then, based on what we tried to explain, make some predictions. So say I saw like the sunrise is already risen before I wake up, right? That's my observation. I could explain like, oh, so I wake up because the sun rises. And then if I wake up because the sun rises, if I cannot see the sunrise, then I won't wake up, right? So that's the prediction that I'm making using my explanation. I can then test it by like locking myself in a room so I can't see the sun. And then if I still wake up, then I know, okay, it's not the sun that wakes me up. Um, Even though it probably does play a part in it, but humans have this circadian rhythm as well, so we're bound to wake up. Or I could be kind of more on the proven side where because I can't see the sun, I sleep in a bit more. I'm like, oh, so then the sun plays a role in waking me up. And then you kind of go back and forth to modify your explanation until it seems like hypothesis is proven or disproven. This is just some examples of like when we're thinking about the atom, what type of things the atom could be. Some general activities that you want to consider when you're doing your science. You'll notice as like observations, though, then explanations, that's what we call like forming a hypothesis. And then testing those, which is our experimentation process. These are some more formal definitions. So a hypothesis can be described as a tentative explanation for some observation, experiment and recreation of an event or occurrence. And then our controlled experiment ideally only has one factor that's really changing. So the rest are kind of as steady as possible. We also tend to have a control group where we can kind of compare that to whatever we're changing. The experimental group is when we're changing something in the experiment. So say if I was trying to see how different food colorings affected the way I made my icing, right? I would make maybe an icing that has no food coloring at all. That would be my control group. An icing that has like liquid food coloring and an icing that has gel food coloring. So the factor that I'm changing is the type of food coloring. I'd be keeping all the other factors like my recipe, the machine I'm making the icing on, the room that I'm making the icing in, all that the same. And the only thing I'm changing is the type of dye I'm adding, or no dye, which is our control group. So important things to remember from this slide is the definition for hypothesis, of it being a tentative explanation for an observation. That is something that is very likely to show up on future like homeworks or quizzes. We did our little practice problem thing, and then this just shows the different words for how light travels through an object. So if it completely passes through a transparent like window, if it kind of passes through, it's translucent. This is commonly like frosted glass window or really cloudy plastic. And opaque is just it does not pass through at all. Or the egg, one of them was translucent too. This slide illustrates how official science requires like a peer review process and usually involves like putting a reputation on the line. So a lot of organizations participate in like specific journals that are well known and kind of vouched for. instead of like an independently published paper. And then you also have to kind of like consider if the person who's saying the pseudoscience has anything to gain from making from the claim. So, for example, if you have like an ad and they're talking about like all the science behind this product and then they're trying to sell you the product, it's most likely pseudoscience that's just meant to be like an advertising ploy. Versus if you read about the impact of, say, like blueberry juice on oxidation levels in the human cells in a paper that is found in a well-renowned and peer-reviewed study or journal, then that's going to be a much more trustworthy like location to find your science. Laws are important relationships that we observe over and over again. So, for example, we've always seen gravity. Gravity always works when we look and we're like, does gravity still work? Yep, it still works. Principles are a bit more descriptive, but also more specific. And it tends to relate to like one or few things, but it's not always a very clear distinction. So the example that we have here is Archimedes' principle relating to object and fluids. It's you can also kind of think of it as like the convention current principle where like heat's gonna rise and cold air's gonna go fall down type of thing. Theories, it's important that you know what a theory is. It's something that we consider to be true because there's a lot of experimental support for it, and it's based on a broad set of hypotheses that have been tested and that are working, that have been found to be working, and have yet to be kind of disproven. I would definitely try to remember the definition of a theory as a broadly based set of working hypothesis. That might also show up on a quiz. And then you have a model, which is just a collection of theories trying to represent a system. So a lot of math um, equations can be models. You can also see these as like sketches and things like that. So like the water cycle is a model of a collection of theories that we know to be true about how water moves through the world, and then trying to represent the physical system of how water moves through the atmosphere and through the soil and things like that. And then I think that's it. This is just if you want more space for some practice on remembering things. This is an example of a model of how we're trying to capture something that happens in real life onto a diagram. And this is some practice if you wanted to practice converting these to like grams and milliliters and then try to make yourself a waffle. That is all, and I hope you have a nice day and take care. See if I can